Let us go to the next separation axiom, that is T 3.5 space. Okay, now for the definition of T 3.5 space, I need completely regular. So let us see what is a completely regular topological space. A topological space X tau is said to be completely regular if and only if given a closed set and an element not belonging to that closed set, there exists a continuous map F from that topological space X to the closed interval 0, 1 such that F of the element goes to singleton 0 and F of the closed set capital F goes to singleton 1. That is the definition of completely regular. Definitions are very, very important. And let us read the definition again. So it says completely regular if and only if whenever you have an element and a closed set, element not in the closed set, there exists a continuous mapping, okay, F from X to the closed interval 0, 1 such that F of the element goes to 0 and F of the closed set will go to 1. What is T 3.5 space? T 3.5 is also called Tichonov. This NOV, V is sounded as double F. Tichonov space. A topological space X tau is T 3.5 or Tichonov space if and only if it is both completely regular and T1. So definitions are very, very important. Now we shall go to prove a theorem. The theorem is to prove that completely regular space is regular. We shall prove that completely regular space is regular. So completely regular is regular. That's what we have to prove. So proof. So let us take a completely regular space. So I'm taking a topological space. Let X tau be a completely regular space. Okay, what we have to prove? TPT to prove that X tau is regular. X tau is regular. So what do I have to prove it is regular? No. So what should I take now? So I'm taking an element belonging to X and F be a closed set such that the element not in the closed set. I'm taking an element not in the closed set. I have to prove what? I have to prove it is regular. So I want two disjoint open sets separating X and capital F. Okay. Now since X is completely regular. So what do you mean by completely regular? Whenever I have an element and I have a closed set, element not belonging to the closed set, and the space is completely regular. So what will happen? There exists a continuous map. We'll call the map as F from where to where? X to 0, 1 such that the element goes to 0 and the closed set will go to 1. Okay, now let us consider the usual topology, okay, on of course the real numbers, and the closed interval 0, 1 is the subspace of R. So I'm going to take the relative topology on 0, 1. Okay, so 0, 1 I'm marking here. This is 0, this is 1. We'll extend it. Okay, we'll divide this interval into three parts. So this is 1 by 3. This is 2 by 3. And we'll extend this. This is real line. Okay, we'll extend this. This point will be minus 1 by 3. And I will take another part of that. That is 4 by 3. This one is 3 by 3. And that is 4 by 3. Okay, so now consider the closed interval 0 and open interval 1 by 3. So closed interval 0 and 1 by 3, it is open here. This is equal to, give me an open interval, okay, intersection 0, 1, so that this will be the common points of those two. I want an open interval. So the open interval will be minus 1 by 3 plus 1 by 3 intersection 0, 1. See, minus 1 by 3 to plus 1 by 3 is this open interval, and 0, 1 closed interval is from here to here, right? So the common points are these. These are the common points. That is this. Okay, so this is an open interval, and in the usual topology, open intervals are nothing but open sets, right? So this definitely is open in R. So tau element intersection Y. So therefore, this is our tau star element. So this is open in 0, 1. Relative topology. Okay, this set is open in 0, 1. Okay, similarly, I'll take another interval. Interval is this. I'll take 2 by 3, and this side it is open and 1 is closed. That is which interval here? That is, I want this and this interval. So I want only this part. So can you give me this as an open interval? Intersection 0, 1. So that is nothing but from here to, I'll take this open interval, full interval. Okay, that is 2 by 3, comma 4 by 3, intersection 0, 1. From here to here, the common points will be these. Okay, right? And this is a tau element here. See, open interval, intersection Y. So therefore, this set is dash, that is open in 0, 1. So I've got two open sets where in 0, 1. I've got two open sets in 0, 1. Are they disjoint? And they are disjoint. See, this open interval and this open interval, no common points at all. So they are disjoint. And 2 by 3 and including 1. So that is, these two intervals are disjoint. I got two open sets in 0, 1. Okay, so next I got two disjoint open intervals in 0, 1. Fine. So next step. And what is our F? F is continuous mapping. Correct now? F is F from X to 0, 1. Okay, is continuous mapping. This is continuous mapping. And I got two open sets in 0, 1. And open sets are what? 0, 1 by 3. And 2 by 3, 1. These two are open in 0, 1. See, I've got two open sets here. Inverse of open sets are open sets because it is continuous map. So inverse, that is F inverse of the open set. Okay, and one more, F inverse of, this is another open set here. So F inverse of that. So these two are open. So these two are open where? Inverses, no? F inverses will be in X. So in X, we got two open sets in X. Okay, so number one, they are open sets. So I got two open sets in X. Are they disjoint? Let us take the intersection F inverse 2 by 3, 1. This side it is open. That is equal to F inverse of, one bracket here, 0, 1 by 3, intersection, 2 by 3, 1. Okay, these two are disjoint, therefore it is F inverse of null set equal to null. So they are disjoint. So we got two open sets and the open sets are disjoint. The open sets are disjoint. Then, okay, third point. Remember, we had to prove it is regular. We had to prove it is regular, and we had taken an element X and a closed set, element not in the closed set. Closed set was F. So I want two disjoint open sets separating X and the closed set F. Okay, now let us see whether X belongs to one of them. Now, since what is F of X? F of X is going to 0, no? Since F of X is equal to 0, okay, so what is X? Belongs to 0, correct? F inverse of 0. And F inverse of 0 is contained in F inverse of, so including 0. So including 0, 1 by 3, open that side. So definitely this is contained in this. So we got X belonging to this F inverse of one of the open sets. And I want another open set. We'll check whether the closed set F belongs to the other open set. So since F of the closed set is going to singleton 1, no? Singleton 1. Okay. So therefore, F inverse of 1, and F inverse 1 is contained in F inverse of, so which is open set containing 1. So it is 2 by 3, 1 is contained in this. So we got F is contained in F inverse of 2 by 3 and 1. Now we'll check all the three. See, I got two open sets in X. They are disjoint. And I got X belonging to one of them and F is contained in the another. So I got two disjoint open sets separating X and F. So therefore, the topological space X tau is regular. Regular. So therefore, completely regular implies regular. So we proved a very, very important theorem and the proof is very, very easy. Now we shall go to the next theorem. The next theorem is to prove that T3 and half implies T3. T3 and half implies T3. Now what do you mean by T3 and half? So proof T3 and half implies completely regular and T1. Okay. What is T3? T3 implies regular and T1. Okay. So T1 is common. T1 is common. So we have to prove that completely regular implies regular. The only thing is we have to prove it is regular. Okay. We have to prove that it is regular. So we have to prove completely regular implies regular. We have to prove that completely TPT completely regular implies regular. This is nothing but the proof of the previous theorem. So this proof is done. So same proof, same as the previous one. The proof of the previous one. Okay. So now we shall go to the next theorem. The next theorem is to prove that T3 and half property is topological. We shall prove that the property T3 and half is topological. Okay, this is a theorem. T3 and half property is topological. T3 and half is also called Tichonov. Tichonov property is topological. Okay, so proof, very, very easy. So let me take, let x tau be T3 and half. Okay, what do you mean by T3 and half? T3 and half implies completely regular and T1. Okay, so first step, we shall prove that TPT, to prove that T1 property is topological. And we have done the proof of this in the previous lecture. This proof is already done. Second step, we shall prove that TPT, what? Complete regularity, complete regularity, complete regularity. This property is topological. We have to prove that this property is topological. Complete regularity is topological. Okay. So what we have to do now? So we want to prove that complete regularity is topological. So I'll take a topological space. Let x tau be completely regular. CR means completely regular. And I'll have to take a homeomorphism. So I'll take G as a homeomorphism from x tau to another topological space y some tau dash. Let this be a homeomorphism. What do you mean by homeomorphism? Bijective. Our G is bijective, G is continuous, and G is open mapping. Okay. Next, we have to prove that, to show that what? Y tau dash is completely regular. We have to prove that the image, homeomorphic image of completely regular space is regular. That means I have to prove that y tau dash is completely regular. So completely regular, no. So I should take one element. So I am taking one element. Okay. And a closed set, element belonging to y. And let us take a closed set. Let B, F be a closed set in y such that the element doesn't belong to the closed set. So what do you mean by completely regular? I want one continuous function, right? From where to where? From this y to 0, 1, such that the element will go to 0 and the closed set will go to 1. So I want a continuous function. Okay, yes. Now we rewrite it. So y doesn't belong to f. So this implies there exists x belonging to capital X such that g of x equal to y. Why this happens? Because our G is a homeomorphism. G is bijective. In that it is onto. So therefore there exists x like this. Okay. And consider G inverse of f. Now where is G inverse f? Definitely in x. And what is G inverse f? G inverse f is dash. Can you guess? It is closed. Why it is closed? Because G is continuous. Why it is continuous? Because G is homeomorphism. Homeomorphism means it is continuous also and takes closed sets to closed sets. And F is closed. F is closed. So inverse of a closed set is closed. Fine. Okay, G inverse F. I got a closed set in F. And I want an element not belonging to this closed set. Right? Okay. What about the element now? Since y doesn't belong to f, since y doesn't belong to f, since y doesn't belong to f, what about G inverse y? So this implies G inverse y will not belong to G inverse f. And what is G inverse y? G inverse y is nothing but x. So this is nothing but x. X doesn't belong to G inverse f. And G inverse f is closed. Okay, in X, and our X or X tau is dash is completely regular. So what will happen now? So therefore, completely regular. So what will happen? There exists, there exists a continuous function. There exists a continuous function. That function we'll call it as f, continuous map. Okay, f from where to where? From x to 0, 1, from x to 0, 1, such that the element is x is going to 0. You can write singleton 0 or 0 itself because only one element here. And the closed set. So f of the closed set here is this, is going to singleton 1. Singleton 1. Okay, because our x tau is completely regular and we use the complete regularity of x for any element and a closed set element not belonging to the closed set, there exists a continuous function. Okay, from x to 0, 1 such that the element is going to 0 and the closed set is going to 1. Okay, actually what I want, we have to prove y is completely regular. Remember, we have taken one element y not belonging to the closed set f. I want a continuous function, okay, from y to 0, 1. We want a continuous function from where to where? From y to 0, 1 such that the element y is going to 0 and the closed set f is going to 1. Okay, I want a continuous function there. Okay, now define h equal to f composition G inverse. So where is this function? Where is f from? F is from where to where? F is from x to 0, 1. And where is G is from? G is from x to y. Correct? X to y. So where is G inverse from? G inverse will be from y to x. So where will be h now? So therefore h should be a function from where to where? So it will be the domain of G inverse, that is y, and codomain of 0, 1. So we got a function. Remember we wanted a function. We wanted a function from where to where? From y to 0, 1. See, I'm getting. Okay. If a function from y to 0, 1. Okay. Such that, number 1, is it continuous? H is continuous. Why it is continuous? Because H is nothing but this. F is continuous, G inverse is continuous because F and G inverse both are continuous. Both are continuous, therefore H is continuous. Composition of any two continuous mappings are continuous, therefore H is continuous. So I got a continuous function. Okay, and it is from y to 0, 1. Okay, now H of the element y. Consider H of the element y. What is H? Will write. So F composition G inverse of y. And that is nothing but F of G inverse of y. F of G inverse of y. Okay. What is G inverse y? G inverse y. Remember our G of x equal to y. So G inverse y is nothing but x. And what is f of x? F of x is nothing but 0. So equal to 0. So I got h of the element y is 0. And let us take h of the closed set. So h of the closed set, in the beginning, we had taken a closed set in y, no? So that is f. So consider h of f. Similarly, so f composition G inverse of f, that is equal to f of G inverse of f. And f of G inverse of f is nothing but 1. So that is nothing but 1. So h of f equal to 1. So I got a continuous mapping from y to 0, 1. And the element is going to 0. And the closed set is going to 1. Right? Therefore, y tau dash is completely regular. So therefore, what have we proved? Complete regularity. Complete regularity is dash topological. This is our step 2. By step 1 and step 2, by step 1 and step 2, what is the conclusion? Step 1 and step 2. What was our step 1? Remember, step 1 was T1 property is topological. Step 2 is complete regularity is topological. So therefore T3 and half property is topological. And that's a proof, and very, very simple proof. We shall go to the next theorem. The next theorem to be proved is T3 and half property is hereditary, or Tichonov property is hereditary. To prove that Tichonov property is hereditary. Okay, this is a theorem to be proved. Tichonov property is hereditary, or T3 and half property is hereditary. Okay, proof. This is also very, very simple proof. So what is Tichonov? That is T3 and half implies completely regular and T1. So step 1, we shall prove that T1 property is hereditary. And this proof is already done in the previous lectures. You can refer that. And step 2, to prove that complete regularity is hereditary. Complete regularity is hereditary. We are going to prove this. Very, very simple proof. So I should take what now? So I'm taking a topological space X tau be completely regular. I'm taking a subspace Y tau star be a subspace of X tau. Okay, so Y is subset of X. And what is our tau star? Tau star contains tau elements intersection Y. What we have to prove now? TPT, or to show that Y tau star is also completely regular. Shall prove that this is also completely regular. So completely regular, no. By the definition of completely regular, what? For any element not in a closed set. What is F? F is a closed set. Where? In Y. In Y. So F is closed set in Y. Take any element not belonging to F. Not belonging to that closed set. Okay. Now since it is closed in Y, so bar is itself. Its closure is itself equal to F. Now since there are two topologies here, tau star and tau, let us denote this is tau star bar. So I'm writing capital Y. Capital Y means it is tau star bar. The closure. Closure is with respect to tau star. So this is equal to F. And by relative topology, tau star closure is equal to tau closure intersection Y. Okay, and this is nothing but F itself. So F equal to F bar intersection Y. Okay, and where is our Y? Our Y doesn't belong to F. So our Y, the element Y doesn't belong to F. So Y doesn't belong to F. but actually y is coming from capital Y. So therefore, see, y doesn't belong to this. So it will not belong to the whole thing. But actually, our y belongs to this. So therefore, y will not belong to f bar. Okay. And what is f bar? Any set bar is closed. Is closed, closed. Where it is closed? I have two topologies here. So where it is closed? Which bar is this? Which closure is this? This is nothing but tau closure. So this is closed in X. This is closed in X. See, I got an element. I have got a closed set. Element not in the closed set. And X is. And X is. What do you know about X? X is completely regular. X is completely regular. I have an element. I have a closed set. Element not in the closed set. Completely regular. So what? So there exists a function. What function? Continuous function. So there exists a function, a continuous function, continuous function. We'll call the function as f. We'll call the function as f. We'll call the function as f. From where to where? From x to 0, 1, x to 0, 1, x to 0, 1. Okay, such that the element is y. Our small y also belongs to x because y is also subset of x, no? As small y is coming from capital Y subset of x. So therefore small y belongs to x only. So the element is going to 0 and the closed set bar is going to 1. Is going to 1. Okay, remember I have to prove y is completely regular. I want a continuous function on y to 0, 1. Okay, now consider f star. F star is nothing but f only restricted to y elements. Let us take the restriction map, restriction function, restriction map. Okay, our f star is nothing but f only, f restricted to y. So f is function from x to 0, 1, and our y is what? Y is subset of x. So I can have a restriction map on y. So this f star is nothing but from y to 0, 1. So f star is a function from y to 0, 1. Now, number 1, is it continuous? F star is continuous because we know that restriction maps, restriction functions or restriction maps of continuous functions of continuous function is continuous. So therefore, f star is continuous. What about the element f star? F star. So remember our y was small y not belonging to f. So small y not belonging to f. F is any closed set in y. Now I want a continuous mapping. Okay, I've got the continuous mapping f star from y to 0, 1. Now we have to prove that f of the element is going to 0 and f of the closed set is going to 1. That's what we have to prove now. So I'm taking f star of y. So f star of y is nothing but f of y because y is coming from capital Y. So whenever you have y elements, for all y elements, f star and f are same. So y belongs to y, capital Y. Therefore, f star of y is nothing but f of y. Okay. And what is f of y? F of y is nothing but 0. F of y is nothing but 0. So therefore, we have got f star of the element is going to 0. Third condition. Consider f star of the closed set f. And where is our f? F is subset of y, no. F is a closed set in y. So f is in y only. So whenever for all y elements, f star is nothing but f only. F of f. And what is f of f? What is f of f bar? See, we have this. F of f bar is going to singleton 1. Now, since f any set is contained in its bar, remember A is contained in A bar. So any set F is contained in F bar, and F of F bar is singleton 1. All the elements in F of bar is singleton 1. So that means F is contained in F of bar. So therefore, F of F elements is also singleton 1. So we have got F star of F is singleton 1. See, F star of the element is going to 0, F star of the closed set is going to 1, and F star is continuous. Okay, so therefore, what is the conclusion now? Therefore, Y tau star